Good afternoon, everyone. I would like to first thank Kilimanjaro for organizing this nice conference, and also INQA for the free waiver. So my name is Alatz Alvarez. I'm from the Basque Country's University. I'm part of INQA Center's researching group. My supervisor is Mikkel Sanz. Some of you might know him. And I will be presenting high-dimensional digital analog quantum computing. To do so, I will first go through an introduction, discussing the most common paradigms for quantum computing. Then I will do a 101 into digital analog quantum computing. I will address the spin operator case. Then I will show how to extend the paradigm beyond SU2 algebra. And I will show a small numerical analysis against the digital quantum computing protocols. So there's two ways of doing quantum computing. We first have the analog quantum computing paradigm, which relies in, I prepare a Hamiltonian in my lab. Usually these Hamiltonians are very robust against noise, but they have kind of a big con, which is they are not universal. You have to tailor the problems to the Hamiltonian instead of using the Hamiltonian for any problem. Then you have digital quantum computing, which is very versatile, it's universal. You can design a set of Clifford gates, and that's it mainly. But it's very prone to environmental errors, especially entangling gates. And it's, you can also find control errors while designing these gates. So the main idea here is taking both sides and joining them so we can get the best of both worlds. We can get the universality that we have in digital quantum computing and the robustness that the analog quantum computing offers. To do so, we will need an entangling operation, which will be given by our Hamiltonian, the one that we have in the lab, and then single qubit gates. Our objective will be to simulate any other Hamiltonian that we want to do, and to do so, we will we will conjugate this Hamiltonian using the single qubit gates. So entangling, for those, conjugating, for those that don't know what it is some sort of sandwiching. You'll see it here. You applied a single qubit gate, then you let your Hamiltonian on, and then you apply the adjoint of the single qubit gates, and so on. There are two ways of doing this. We have the stepwise digital analog paradigm, which consists of I apply the gates, I switch on the Hamiltonian, then I switch it off afterwards, and rinse and repeat. So this is not the best when it comes to experimental implementations, because we are taking into account that we can use the sudden approximation, and it's very limiting. So we will only use this mainly for our analysis and to solve the problem. For implementations, we will use the bank digital analog paradigm, which will be, I let my Hamiltonian on all the way through my experiment, and I will apply the pulses in between. Now, this has a little bit of an error because you have the dynamics at the same time as the pulses, but it's usually much better than just turning on and off the Hamiltonian. So the main idea, given a Hamiltonian, a problem Hamiltonian, by, let's say, Ising Hamiltonian, for example, and another source Hamiltonian that is similar to it with different couplings, we will conjugate it with polymatrices for the case of qubits, and we will consider all the possible conjugations that we can do, and we will try that the product of these conjugations to come as close as we can to the evolution we want to implement. When we conjugate a Hamiltonian, what we are doing is turning it into an effective Hamiltonian. Because for the qubit case, what we are doing here is switching the signs. As an example, for the source Hamiltonian in the first block, we'll see that if we apply the X poly gates, any coupling that has the first qubit will change the sign, except if the coupling is given by the poly X. So our first approximation will be, we'll turn this product into a sum of all the effective Hamiltonians. If they do not commute, we will trotterize afterwards. And then we will solve this sum of Hamiltonians for the times that they need to evolve. This will turn our problem into a linear system of equations where we want to get all positive solutions because they don't make any sense if not. As an example, here's an Ising Hamiltonian of 3 qubits that are all coupled amongst themselves. And we can see here that if we conjugate, for example, the qubits 1 and 3, we are changing the effective signs of the coupling 1, 2, and 2, 3. And we are not doing anything to the coupling 1, 3 because, I mean, we are flipping both signs, so we are actually doing nothing. And we represent that in our matrix M, where the rows are given by the different elements of the Hamiltonian. To do this in a more general way, there's a protocol for arbitrary two-body Hamiltonians, which consists mainly in considering all the possible conjugations with the elements in the bases. For example, if I want to conjugate 2 qubits at the same time, I will be conjugate them with the XX, then with the XY, and so on. And I will construct this matrix for all these possible conjugations. And this protocol guarantees that I will find a solution and that it will be positive. Now, we wanted to extend this into the qubit case, and the easiest way to start this problem is by considering an spin Hamiltonian. So the spin Hamiltonian, it showcases SU2 algebra dynamics. So it will be the same as with qubits. We only need to find a generator in this basis that changes our sign. So if we do the product with the generators, we'll see that if we set the angle to pi, we will recover the equivalence no matter what dimension we're working with, because we are just flipping the sign here. But for more complex cases, for example, if I have the spin to the power of 2, let's say, I cannot rely only on SU2 dynamics. So we will use the WeylHeisenberg operator basis. That is a product between the clock operator. It's an operator that physically, what it does is give us different phases depending on the energy level, and a shift operator that changes these energy levels. This is part of, it has Clifford algebra properties, which means if I conjugate it, I will get an element of the basis and a phase. If we do this for d equals 2, we will recover our qubit paradigm, so it shows that we are in the right track. And the main changes here now are that our matrix, instead of being full of ones and minus ones, it will be full of the roots of the number here, the omega. An example of this basis is showcased here. And as you can see, if I do the conjugation product, I will get the same element and just a phase. To showcase how this works, I picked the isotropic bilinear biquadratic Ising-like Hamiltonian for spin 1. And from having just a spin Hamiltonian, I will show how to get the quadrupolar term. First, I need to decompose my operators into my bases. As you can see, the decomposition is not very hard to do, and I get the different elements from the WeylHeisenberg basis. Then I consider all the possible conjugations. For this case, there are only 9 possible conjugations. And if you see, for example, the second possible conjugation, I'm operating only in the first qubit in this case. And you see how I'm adding a different phase depending on which coupling I have. I represent this in my matrix column, and then I construct M. This is my system of equations, and those are the couplings that we want to solve for this problem. And now I will show how some results, numerical results for 6 qubits. I will use the specs. You can see them here. And as you can see, against the digital quantum paradigm, it shows some improvement before getting to the angle pi.5, mainly because we need to employ more gates afterwards, because we are changing the signs for the spin operator, which is very costly. But since the relaxation time is quite high, we are only showcasing here that the errors depend on the amount of qubits that we are implementing, the single qubit gates. It makes quite sense, the result. You can see that the error is constant regarding the gates, and it only moves because of the relaxation time. If you see the total time of simulation, you'll see that when it goes down, my fidelity goes up. So we'll see, as a summary, we have extended the digital analog framework for a qubit system, and it only requires at most a polynomial number of blocks. We've already done solved the spin system case, which is even simpler than for a general D-level system. With this way, we can implement quantum algorithms by only using the clock and shift operators and an entangling Hamiltonian, which simplifies what we need to employ for qubit systems, instead of having to argue or discuss about what kind of gates we should employ. We have some sort of general idea here. Now we can simulate with digital analog bosonic systems that don't need weird mappings. We don't need many qubits to do the mappings. We can just simply use the qubit systems. This also shows that we have an important task here would be reducing total errors, because they scale with the qubit numbers and the dimension of these qubits. Now it's even more costly than it was before. So finding a way of getting these errors out of the picture, it seems to be our main goal. And I would say that is all. And thank you for listening.
Very good. So we have time for 2 questions.
In the beginning, you said in analog quantum computer, it's less prone to noise. I am not so sure why that is. If this is based on a similar physical system,
I mean, yes, yes, it's a very similar system, but usually you have more of a natural entangling Hamiltonian in your system. But if you want to design a Clifford set of gates, you might need to do very weird in-between design choices that reduces the fidelity a lot. So usually the main constraint is I have my Molmer-Sorensen, for example, and I want to design any other gate with Molmer-Sorensen. You have to do decompositions that are very costly. But here you'll have your Hamiltonian, and you mainly will find the relaxation, the damping error, and that's it.
Yeah, okay. Yeah, if the system becomes large, based on the similar physical system, it decohere faster.
Yes.
Usually.
Yeah, I agree. This is mainly for a few qubits systems. It's more tailored to NISQ-era computers than anything else. If you increase the number of qubits, because the error is exponential, usually the digital one that is polynomial will scale better. Yes.
Okay. Good. And there was one last question there. Okay. So let me check how we on time. So as we have time for one last question, I wanted to ask you, Alatz, so in that slide that you had, the one that you were comparing the two paradigms.
It's just that I need the photo for the ministry. Yes.
Yeah, don't worry.
Yeah.
So basically, no, you mentioned that there are two ways to implement this in practice. One is switching on and off the Hamiltonian, the interacting Hamiltonian, right? Yes. And the other one is just keeping the HS Hamiltonian turned on, and then you kind of switch on and switch off the single qubit gates, right? So do you know if this has been implemented in practice with some platform?
So I think it has, but I don't remember the paper now. Sorry. But we are also thinking on using now Donostia's quantum computer and to implement it there.
Okay, thank you. So thank you, Alatz, for this very nice talk. And now we will have, please.